Look at Venus on a clear night. It is the brightest object in the sky after the moon. It outshines every star. It is visible in daylight if you know exactly where to look. Ancient civilizations tracked it as a god, a calendar, a navigational reference. It is one of the most visible and most observed objects in the history of human astronomy. It is also the most terrifying planet in the solar system. Not because of what it is now, because of what it was, and because of what it tells you about the planet you are standing on. Venus is approximately the same size as Earth, same mass, same density, same bulk composition, same distance from the same star at formation, same initial inventory of water, carbon, nitrogen. For the first billion years of the solar system's history, Venus and Earth were, from the outside, almost indistinguishable. Two rocky planets in the inner solar system, both with the raw materials for oceans, atmospheres, and potentially life. Today, Venus has a surface temperature of 465 degrees Celsius, not at the equator, not in summer, not at the hottest point, everywhere, all the time, day and night, pole to pole. The surface temperature of Venus is more stable and more uniform than any environment on Earth. It is also hot enough to melt lead. Its atmospheric pressure at the surface is 92 times Earth's God, equivalent to being 900 meters underwater in Earth's oceans. Its atmosphere is 96.5% carbon dioxide. Its clouds are made of sulfuric acid droplets. It rains sulfuric acid in the upper atmosphere, though the rain evaporates before reaching the surface because the surface is too hot even for sulfuric acid to remain liquid. It rotates backwards relative to Earth. Its day is longer than its year. Its surface is dominated by volcanic plains and hundreds of volcanoes, some of which may still be active. And it did this to itself. Through a process that began with the same initial conditions as Earth, through a feedback loop that, once started, could not be stopped, through what planetary scientists call the runaway greenhouse effect. The same process has already started on Earth, not at Venus scale, not yet, but the mechanism is the same, the physics is the same, the direction is the same. In this video, we are going to go through exactly what happened to Venus, how we know it was once more like Earth, why the runaway greenhouse occurred, and what the current trajectory of Earth's atmosphere looks like when measured against the same physical framework. There is something in the fifth section of this video that most climate scientists describe as the most important number in planetary science, not because it is the current carbon dioxide concentration, not because it is the current temperature, but because it is the threshold, the point beyond which the feedback becomes self-sustaining and cannot be reversed by any process available to a planet without deliberate intervention. That threshold has a name, it has a value, and where Earth currently sits relative to it is the most important fact in this video. Stay with me. Before we continue, Venus and Earth formed from the same protoplanetary disk, at similar distances from the same star, with similar initial compositions. One has oceans, complex life, and a habitable surface. The other has 465-degree surface temperatures and sulfuric acid clouds. Drop a comment with what you think is the single most important difference that led to these two outcomes. We will come back to whether you were right. Let's start with what we actually know about Venus's past, what the evidence says rather than what we might assume. The direct evidence for Venus's early history is limited. Venus's surface is geologically young. The visible surface dates to approximately 500 to 700 million years ago, based on crater counting and volcanic activity estimates. Whatever geological record existed from the first 3 billion years of Venus's history has been largely overwritten by subsequent volcanic activity. This makes Venus's early history difficult to reconstruct directly. What we have instead is a combination of theoretical modeling, comparison with Earth's early history, isotopic evidence from the current Venusian atmosphere, and the general framework of planetary formation physics. What the evidence suggests is the following. Venus almost certainly had water in its early history. The planet formed from the same population of planetesimals as Earth, rocky bodies that contained water ice and hydrated minerals. The delivery of water to the inner solar system by these planetesimals was not selective. Venus received water in similar quantities to Earth, given its similar mass and similar orbital history during the late heavy bombardment period. The question is not whether Venus had water, it almost certainly did. The question is in what form, for how long, and how much. The current Venusian atmosphere contains a ratio of deuterium to hydrogen, heavy hydrogen to normal hydrogen, that is approximately 150 times higher than Earth's ratio. This isotopic signature is a fossil of Venus's water history. Deuterium and hydrogen are both forms of hydrogen. They have the same chemical properties but different masses. Deuterium is heavier. When water escapes to space, when ultraviolet radiation breaks water molecules apart and the hydrogen atoms escape the planet's gravity, the lighter hydrogen escapes more readily than the heavier deuterium. Over time, the remaining hydrogen becomes increasingly enriched in deuterium relative to the original ratio. The current deuterium to hydrogen ratio on Venus, 150 times Earth's, implies that Venus once had significantly more water than it currently does. The water was lost to space over time through this process of preferential hydrogen escape. The amount of water implied by this ratio is uncertain. Some analyses suggest Venus may have had enough water for a shallow global ocean, perhaps a few hundred meters deep on average. Others suggest the water inventory was smaller, enough for substantial surface moisture, but not a deep global ocean. Whether Venus had a global ocean at any point remains debated. What is not debated is that it had significantly more water than it currently does, and that the water was lost over geological timescales through a process driven by changes in atmospheric composition and temperature. This is the key point. Venus did not form dry. It had water. It lost that water. And the mechanism by which it lost that water is the same mechanism that could, under specific conditions, affect Earth. The deuterium to hydrogen ratio on Venus was first measured by the Pioneer Venus probe in 1978 and subsequently refined by the Soviet Venera landers and the European Space Agency's Venus Express mission. The current best estimate of the DH ratio on Venus is approximately 0.016, compared to Earth's ocean water value of approximately 0.000156, a ratio of approximately 100 to 150 times higher on Venus. The enrichment is interpreted as evidence of significant water loss through photodissociation and hydrogen escape over geological timescales, though the initial water inventory implied by this ratio depends on assumptions about the escape rate and initial composition. There is a specific piece of evidence from the current Venusian atmosphere that makes the early Venus story more concrete. Venus Express, the European Space Agency's orbiter that operated at Venus from 2006 to 2014, detected evidence of recent volcanism on Venus's surface. Thermal emission data from VIRTIS, the Visible and Infrared Thermal Imaging Spectrometer, showed regions with anomalously high thermal emission, consistent with fresh lava flows. The freshness of these flows, fresh in the geological sense, meaning not significantly weathered, suggested volcanic activity within the last few tens of thousands to millions of years. A 2023 paper by Robert Herrick and Scott Hensley, analyzing archival radar images from the Magellan spacecraft taken in the early 1990s, reported the detection of a volcanic vent that changed shape between two observations separated by 8 months, consistent with a volcanic eruption occurring between the two observations. Venus is volcanically active today. Its interior is still generating heat. Its geological processes are ongoing. This matters for the early Venus story because an active interior implies ongoing volcanism, and ongoing volcanism implies ongoing outgassing, the release of gases from the interior into the atmosphere. The composition of a planet's atmosphere is a balance between outgassing from the interior and removal processes, chemical weathering, escape to space, and absorption into the surface. On Earth, the carbon dioxide outgassed by volcanoes is removed from the atmosphere by the carbonate-silicate cycle, a geochemical feedback in which carbon dioxide reacts with silicate rocks in the presence of liquid water to form carbonate minerals, which are eventually subducted into the mantle and recycled. This cycle acts as a long-term thermostat for Earth's climate, keeping surface temperatures within the range where liquid water exists. On Venus, this cycle broke down. The question is why? The greenhouse effect is not a catastrophe. On Earth, it is a necessity. Without any greenhouse effect, Earth's average surface temperature would be approximately negative 18 degrees Celsius, well below the freezing point of water. The greenhouse gases in Earth's atmosphere, primarily water vapor, carbon dioxide, and methane, absorb infrared radiation emitted by Earth's surface and re-emit it in all directions, including back toward the surface. This energy redistribution raises the average surface temperature to approximately 15 degrees Celsius. The greenhouse effect is the difference between a frozen, lifeless planet and the world you live on. The greenhouse effect becomes catastrophic when it runs away. A runaway greenhouse effect occurs when a positive feedback loop becomes self-sustaining. Water vapor is a powerful greenhouse gas, more powerful than carbon dioxide on a per-molecule basis. As temperature increases, more water evaporates from the surface, increasing the water vapor concentration in the atmosphere, which increases the greenhouse effect, which increases the temperature further, which evaporates more water. This feedback exists on Earth today. It is not run away because there is a negative feedback that stabilizes it. As water vapor increases, cloud cover increases. Clouds reflect incoming solar radiation. They have a cooling effect that partially offsets the warming effect of water vapor. The net result, on Earth, is a system that responds to perturbations but returns to equilibrium. On Venus, something broke this equilibrium. The precise timing and mechanism are debated. The most widely accepted model involves the gradual brightening of the young sun. When the solar system formed 4.6 billion years ago, the sun was approximately 70% as luminous as it is today. Over 4.6 billion years, stellar evolution has increased the sun's luminosity by approximately 30%, the same brightening that we discussed in the video about the sun's death and Earth's future. Venus is approximately 28% closer to the sun than Earth. It receives approximately 1.9 times as much solar radiation per unit area as Earth. When the sun was younger and dimmer, this difference may have been manageable. Venus's greater distance-compensated radiation budget may have been compatible with liquid water on the surface. As the sun brightened, the radiation balance on Venus shifted. The surface temperature rose slightly. Slightly higher temperatures caused slightly more water evaporation. Slightly more water vapor in the atmosphere increased the greenhouse effect slightly, which raised the temperature slightly more, which evaporated more water. At some point, models suggest between 1 and 3 billion years ago, the feedback crossed a threshold. The rate of water vapor increase exceeded the rate at which cloud formation and other negative feedbacks could compensate. The feedback became self-sustaining. The runaway greenhouse was underway. Once the runaway begins, it cannot be stopped by any process internal to the planet. The feedback accelerates. Temperatures rise. More water evaporates. More greenhouse warming. Higher temperatures still. The process continues until the oceans are completely evaporated. When the oceans are gone, the water vapor reaches the upper atmosphere. Ultraviolet radiation from the sun breaks the water molecules apart. Photodissociation. The hydrogen atoms escape to space. The oxygen atoms remain, initially, but eventually combine with surface minerals through oxidation. The water is gone, permanently, not recycled, destroyed, broken into its component elements, the hydrogen lost to space, the oxygen absorbed by the rocks. Without water, the carbonate-silicate cycle, Earth's carbon dioxide thermostat, cannot function. There is no liquid water to dissolve carbon dioxide, no rain to carry carbonic acid to silicate rocks, no chemical weathering to produce carbonates. The carbon dioxide outgassed by volcanism accumulates in the atmosphere, adding to the greenhouse warming. The temperature rises further. The current Venusian atmosphere, 96.5% carbon dioxide, surface temperature 465 degrees Celsius, atmospheric pressure 92 times Earth's, is the endpoint of this process. The accumulated carbon dioxide of billions of years of volcanism with no water to remove it, producing a greenhouse effect so extreme that the surface temperature exceeds the melting point of lead. The runaway greenhouse effect on Venus was first analyzed theoretically by James Pollock in 1971, and subsequently developed in detail by James Casting, whose 1988 paper in Icarus, Runaway and Moist Greenhouse Atmospheres and the Evolution of Earth and Venus, established the theoretical framework that is still used today. Casting identified two distinct runaway greenhouse thresholds: the moist greenhouse, in which water vapor reaches the stratosphere and is lost to space while liquid water remains on the surface, and the runaway greenhouse, in which all surface water evaporates. The solar flux threshold for the runaway greenhouse on an Earth-like planet was estimated at approximately 1.4 times Earth's current solar flux, a value Venus currently exceeds by approximately 35%. Let's describe what Venus's surface actually looks like now, because the description makes the scale of the transformation concrete. The Soviet Union landed 9 spacecraft on Venus's surface between 1970 and 1982 as part of the Venera program. These were extraordinary engineering achievements. The Venera landers were designed as pressure vessels, essentially submarines built for atmospheric pressure, capable of surviving the 92 atmosphere pressure and 465-degree temperature of the Venusian surface. The survival time was short. Despite the extraordinary engineering, the landers typically function for between 23 minutes and 2 hours before failing. The combination of extreme temperature and pressure degrades electronics and materials in ways that cannot be indefinitely prevented. But in those minutes to hours, the Venera landers transmitted images and data from the surface of Venus. The images show a desolate, flat landscape of dark basaltic rock, illuminated by a dim orange-red light, sunlight filtered through the dense yellow-orange clouds of the Venusian atmosphere. The sky, as seen from the surface, is not black or blue. It is a murky orange, like a perpetual dense smog. There are no mountains in the Venera landing images. The landers set down on the volcanic plains that cover much of Venus's surface. The rocks are flat slabs, dark and seemingly fresh, though that freshness is relative, on a planet where the surface is continuously baked at 465 degrees. Surface processes that would weather rocks on Earth operate differently. The temperature does not vary between day and night. Venus's rotation is so slow, one Venusian day equals 243 Earth days, and its atmosphere so massive and thermally stable that the day side and night side are nearly identical in temperature. The atmosphere acts as an enormous thermal buffer, distributing heat around the planet with extraordinary efficiency. The atmospheric circulation on Venus is driven not by the temperature difference between day and night, that difference is negligible, but by the interaction between solar heating of the upper atmosphere and the planet's slow rotation. At cloud level, approximately 50 to 70 kilometers above the surface, winds reach 360 kilometers per hour, circling the entire planet in approximately 4 Earth days, despite the planet's 243-day rotation. The clouds themselves, made of sulfuric acid droplets, are visually striking from space. Venus appears as a featureless white-yellow disk in optical images, its surface completely hidden by the unbroken cloud layer. The clouds reflect approximately 70% of incoming sunlight, making Venus extremely bright as seen from Earth, but also reducing the solar radiation reaching the surface. This reflectivity, the high albedo of Venus's sulfuric acid clouds, partially compensates for Venus's proximity to the Sun. Without the clouds, Venus's surface would be even hotter. With them, the solar radiation reaching the surface is reduced to levels comparable to what Earth receives. But the greenhouse effect from the 96.5% carbon dioxide atmosphere overwhelms this reduction. The small fraction of solar radiation that does reach the surface heats it. That heat is trapped by the carbon dioxide atmosphere almost completely. The carbon dioxide absorbs infrared radiation across essentially the entire spectrum relevant to the surface temperature. The surface cannot radiate its heat to space. The temperature builds, 465 degrees Celsius, everywhere, always. This is what happens to a planet when the carbonate-silicate cycle breaks down. The oceans evaporate, the carbon dioxide accumulates, and the greenhouse feedback runs to completion. It starts with liquid water. It ends with a surface hot enough to melt lead, under an atmosphere that would crush a submarine, beneath clouds of sulfuric acid. The Venera 13 lander, which touched down on March 1, 1982, returned the most detailed surface images of any Venera mission, along with spectral data and soil composition measurements. It survived for 127 minutes on the surface, the longest of any Venera lander, before succumbing to the extreme conditions. The temperature measured at the surface was 457 degrees Celsius, and the pressure was 89.5 atmospheres. The soil composition was similar to terrestrial basalt, consistent with a volcanic origin. The Venera program remains the only successful series of landings on Venus's surface. NASA's Da Vinci Plus and Veritas missions, and ESA's Envision mission, are planned for the 2030s and will provide new data on Venus's surface and atmosphere. Stop here. The Venera landers was the most extreme planetary surface missions ever completed, survived between 23 minutes and 2 hours on Venus before failing. The combined operating time of all 9 successful Venera landers on Venus's surface is approximately 10 hours. That is our total direct experience of the most Earth-like planet in the solar system. If you were designing the next Venus surface mission, knowing it would fail within hours, what single measurement or observation would you prioritize? Drop your answer below. Now let's address the question that makes Venus's history most unsettling for Earth. Was there ever a period when Venus was habitable? The answer is possibly. Possibly for a very long time. A 2016 paper by Michael Way and colleagues at the NASA Goddard Institute for Space Studies modeled Venus's climate under early solar conditions, when the sun was approximately 70% as luminous as today, and found that Venus could have maintained habitable surface temperatures for approximately 2 to 3 billion years. 2 to 3 billion years of potentially habitable conditions. For context, the first microbial life on Earth appears in the fossil record approximately 3.5 billion years ago. Complex multicellular life first appears approximately 600 million years ago. The entire history of animal life fits within the last 600 million years. If Venus had 2 to 3 billion years of habitable conditions, from approximately 4 billion years ago to approximately 1 to 2 billion years ago, there was ample time for the emergence of microbial life. By analogy with Earth, where life emerged within the first billion years of the planet's history, a billion-year habitable window is sufficient. This does not mean life existed on Venus. It means the conditions were not obviously incompatible with it. What ended the habitable window was the brightening sun. As the sun's luminosity increased over billions of years, the solar radiation received by Venus crossed the threshold at which the runaway greenhouse became inevitable. The transition may have been gradual, taking tens to hundreds of millions of years, or it may have been more abrupt, triggered by a specific event such as a large volcanic episode that increased atmospheric carbon dioxide above a critical level. The 2016 Wei et al. Paper modeled a slow rotator version of early Venus, assuming Venus's slow rotation rate has persisted since formation, and found that even with slow rotation, the climate could have been maintained in a habitable state for billions of years with the right initial conditions. If Venus was habitable for billions of years, and if life emerged on early Venus, even microbial life, then the question of what happened to that life during the transition to the current hellscape is deeply unsettling. Life does not simply stop when conditions become uninhabitable. It adapts, retreats to refugia, and evolves to survive in whatever marginal environments remain. As Venus's surface temperature rose and the oceans began to evaporate, the surface became increasingly hostile. But the atmosphere, specifically the cloud layer, became a potential refuge. At altitudes of approximately 48 to 60 kilometers above Venus's surface today, the temperature and pressure are approximately 0 to 70 degrees Celsius and 0.4 to 2 atmospheres, conditions that are, in physical terms, within the range tolerated by some extremophile organisms on Earth. A 2020 paper by Jane Greaves and colleagues in Nature Astronomy reported the detection of phosphine, a gas molecule associated with biological processes in the absence of known abiotic production mechanisms, in Venus's atmosphere at cloud altitudes. The detection was subsequently contested. The data analysis was revised. The current status of the phosphine detection is that the signal is not confirmed, but also not definitively excluded. The phosphine controversy generated enormous attention because it raised the possibility, however unlikely, that Venus's clouds might harbor microbial life that survived the transition from the habitable surface to the current hellscape. Life that has been living in the clouds of Venus for billions of years, while the surface became uninhabitable below it, this remains speculative. The phosphine detection is contested. There is no confirmed evidence of life in Venus's atmosphere, but the possibility that life emerged on a once habitable Venus, survived in the clouds as the surface became hostile, and may persist there today, is physically consistent with what we know about Venus and about the limits of life on Earth. The answer to whether it is true requires going there, landing in the clouds, measuring, finding out. We have not done that. The total combined surface time of all human-made objects on Venus is approximately 10 hours. The Wei et al. 2016 paper, Was Venus the First Habitable World of Our Solar System?, published in Geophysical Research Letters, used the GISS Model E, General Circulation Model, to simulate Venus's climate under early solar conditions with a shallow ocean and slow rotation. The study found that Venus could have maintained mean surface temperatures between 20 and 50 degrees Celsius for approximately 2 to 3 billion years with liquid water on the surface, if the initial water inventory was sufficient. The transition to the current state was modeled as driven by increasing solar luminosity crossing the moist greenhouse threshold. The paper is among the most cited in Venus climate science and motivated renewed interest in Venus missions. Now let's talk about Earth and the threshold. The carbonate-silicate cycle, the geochemical feedback that keeps Earth's carbon dioxide levels in a range compatible with liquid water, works only when liquid water exists on the surface. The cycle requires rain. Rain requires liquid water in the atmosphere. Liquid water in the atmosphere requires surface temperatures within a specific range. If surface temperatures rise above a critical level, the water vapor feedback, the same feedback that destroyed Venus, begins to dominate. More water evaporates. More water vapor in the atmosphere increases the greenhouse effect. The temperature rises further. On Earth, this feedback is currently stabilized by cloud feedbacks and other negative feedbacks that keep the system in equilibrium. But the stabilization is not absolute. There's a threshold beyond which the positive feedback dominates. James Casting's 1988 paper established the theoretical threshold for the runaway greenhouse on an Earth-like planet. The threshold is defined by the solar flux, the amount of solar radiation per unit area received by the planet. For an Earth-like planet with Earth's atmospheric composition, the runaway greenhouse threshold is approximately 1.4 times Earth's current solar flux. Venus currently receives approximately 1.9 times Earth's solar flux. It crossed the runaway greenhouse threshold billions of years ago. Earth currently receives 1.0 times Earth's solar flux. It is below the threshold. But the sun is brightening by approximately 1% every 100 million years. Earth's solar flux is increasing. In approximately 600 million years, the timescale we discussed in the video about the sun's death, the solar flux reaching Earth will approach the moist greenhouse threshold. Complex plant life becomes impossible. In approximately 1.1 billion years, liquid surface water becomes impossible. This is the natural trajectory under stellar evolution alone. It does not account for what humanity is doing to Earth's atmosphere right now. The current carbon dioxide concentration in Earth's atmosphere is approximately 420 parts per million. In pre-industrial times, before 1750, it was approximately 280 parts per million. The increase is entirely due to human activity, primarily the burning of fossil fuels. 420 parts per million is not close to the Venus scenario. Venus's atmosphere is 96.5% carbon dioxide, approximately 965,000 parts per million. Earth is nowhere near that level. The current carbon dioxide increase is not triggering a runaway greenhouse, but the physics of the greenhouse effect is not linear. Small changes in forcing can produce large changes in temperature under some conditions, and the direction of Earth's current trajectory, increasing greenhouse gas concentrations, increasing temperatures, increasing water vapor, increasing positive feedbacks, is the same direction as the process that destroyed Venus. The distinction between a manageable greenhouse warming and a runaway greenhouse is not a matter of current carbon dioxide levels. It is a matter of whether the feedbacks are dominated by positive or negative responses. Currently, negative feedbacks, particularly cloud feedbacks, prevent the runaway. The question is how robust those negative feedbacks are to continued forcing. This is the most important open question in Earth's climate science. Not whether the climate is warming, it is. Not whether humans are causing it, they are. But whether the feedbacks are robust enough to prevent a cascade towards something that, while not Venus scale on any human timescale, could produce conditions that make large regions of Earth uninhabitable within centuries. Venus is not a warning about the future of Earth on a human timescale. It is not a warning about the next century or the next millennium. It is a warning about what happens when feedbacks overwhelm stabilizing mechanisms, when a system that was in equilibrium crosses a threshold and is pushed into a new equilibrium that is catastrophically different from the one it left. The threshold that destroyed Venus was a stellar flux threshold, an increase in solar radiation that crossed the point at which water vapor feedback dominated. That threshold is set by astrophysics and is not within human influence on any meaningful timescale. The threshold that matters for Earth on human timescales is different. It is set by greenhouse gas concentrations, by cloud feedbacks, by ice albedo feedbacks, by permafrost carbon release, by ocean circulation changes. It is set by processes that are partially within human influence. Where exactly that threshold is, how much warming, how much forcing, how much feedback amplification, is the central question of climate science. It does not have a single agreed numerical answer. The uncertainty range is wide. The direction of the risk is clear. Venus crossed its threshold. Everything after that was physics. Casting's 1988 Icarus paper, Runaway and Moist Greenhouse Atmospheres and the Evolution of Earth and Venus, established the theoretical solar flux thresholds for the moist greenhouse, approximately 1.1 times Earth's current flux, and the runaway greenhouse, approximately 1.4 times Earth's current flux. Subsequent work by Koperapu et al. 2013 in the Astrophysical Journal refined these estimates using improved atmospheric models, finding the runaway greenhouse threshold at approximately 1.06 times Earth's current flux for a modern Earth atmosphere, slightly closer than Casting's estimate. The inner edge of the habitable zone is defined by the runaway greenhouse threshold, and its precise location has significant implications for the number of potentially habitable planets around other stars. Venus changes how we think about the search for life in the universe. For decades, the search for habitable planets has been organized around the concept of the habitable zone, the range of distances from a star at which a planet's surface temperature allows liquid water. Earth is in the habitable zone. Mars is at the outer edge. Venus is inside the inner edge. But Venus was not always inside the inner edge. For the first 2 to 3 billion years of the solar system, Venus was in the habitable zone. It was in the habitable zone for longer than complex life has existed on Earth. This has a direct implication for exoplanet searches. When we identify an exoplanet in the habitable zone of its star, a potentially Earth-like planet at the right distance, we cannot assume it is currently habitable. We cannot even assume it is currently in the habitable zone. Stellar luminosity increases over time. A planet that is in the habitable zone today may have been outside it earlier. A planet that is outside the inner edge of the habitable zone today, like Venus, may have been inside it for billions of years in the past. The habitable zone is not a static condition. It is a moving target, changing as the star evolves. More fundamentally, Venus demonstrates that being in the habitable zone is necessary, but not sufficient for long-term habitability. Venus was in the habitable zone. Something happened. The habitability ended. The something, the runaway greenhouse, is a physically plausible process that could occur on any planet in the habitable zone if the conditions are right. This means that estimates of the number of habitable planets in the galaxy, estimates that are based on the fraction of stars with planets in the habitable zone, may be overestimates. Not every planet in the habitable zone remains habitable. Some of them go the way of Venus. How many? We do not know. The fraction of habitable zone planets that undergo runaway greenhouse events depends on the distribution of planetary properties, initial water inventory, atmospheric composition, rotation rate, geological activity that we cannot currently measure for most exoplanets. Venus is the one data point we have for a planet that was habitable and became uninhabitable through an internal process. One data point is not enough to estimate a fraction, but it is enough to establish that the process is real, that it happened in our own solar system, and that any estimate of the prevalence of habitable worlds that ignores it is incomplete. The search for life elsewhere in the universe is the search for the conditions that allowed life to persist, not just to begin, but to persist for the billions of years required for complexity to develop. Venus demonstrates that beginning conditions and persisting conditions are not the same thing. A planet can have all the right starting conditions and still end up with a surface temperature of 465 degrees Celsius. What made Earth different from Venus, what allowed Earth to maintain liquid water and a habitable surface for 4.5 billion years, while Venus did not, is not fully understood. The difference in solar flux, the difference in initial water inventory, the role of plate tectonics, the role of the moon in stabilizing Earth's axial tilt, the specific timing of the sun's brightening relative to the planetary properties of both worlds, all of these factors contributed. We got lucky in a specific, measurable planetary science sense. The right conditions, the right distance, the right initial composition, the right geological history, the right stellar evolution timeline relative to those conditions. Venus got unlucky, or got lucky for 2 to 3 billion years and then ran out. Look at Venus on a clear night. It is the brightest object in the sky after the moon. It is beautiful. It is named after the goddess of love. Ancient civilizations tracked it as a divine object. It is a planet where the surface temperature is 465 degrees Celsius, where the atmospheric pressure is 92 times Earth's, where the clouds are made of sulfuric acid, where it may not have rained liquid water for 1 billion years. It is also the planet that was, for perhaps 2 to 3 billion years, something that looked a great deal like Earth, that had liquid water, that had a reasonable surface temperature, that had, possibly, the conditions for life. The process that destroyed it was not a sudden catastrophe. It was a feedback loop, a slow crossing of a threshold, physics taking its course once the stabilizing mechanisms were overwhelmed. Earth is not on the same trajectory on any human timescale. The runaway greenhouse threshold that Venus crossed requires a solar flux approximately 40% higher than Earth currently receives. We are not there. We will not be there for hundreds of millions of years under natural stellar evolution. But the direction is worth understanding. The mechanism is worth understanding. The threshold concept, the idea that a climate system can be in stable equilibrium and then cross a point beyond which the feedbacks push it to a new and very different equilibrium, is worth understanding. Venus crossed its threshold. The physics did the rest. Earth has not crossed its threshold. What happens next depends, in part, on processes that are within human influence. Venus is not a prediction for Earth. It is a demonstration of what a threshold crossing looks like from the outside, on geological timescales, from the perspective of the planet that crossed it. It looks like the brightest object in the night sky. It looks like nothing went wrong. One question. If Venus had a habitable surface for 2 to 3 billion years, enough time for life to emerge and possibly for complex life to develop, and if the phosphine detection in Venus's clouds is eventually confirmed as biological in origin, what would that mean for the Great Filter? We discussed the Great Filter earlier in this series. A second independent origin of life in our own solar system changes the calculation dramatically. Drop your answer below, and tell me whether it makes you more or less optimistic about life elsewhere. Next video. What closed time-like curves are, solutions to Einstein's field equations that permit travel to the past, why they exist in the mathematics of rotating black holes, and why the Gödel universe, presented to Einstein in 1949, was the result that Einstein refused to accept for the rest of his life. See you there.